Good morning. Can you hear me?
Good morning. Good morning.
Okay, yeah. Let's wait for 1 minute or two. I'm letting students in. Oh, yeah. So
Yes.
yeah, let's wait a little bit. Share. I'm recording this. Students one at a time. 4 students coming in. Just a couple minutes, please. Couple minutes. A couple minutes, and we'll start maybe 33. Now we have 11:31, so maybe 11:33. 2 more minutes. Right. So one more minute, we'll start. Guys, we'll start finishing chapter 1, and then I have a condensed PowerPoint for chapter 12 and 2. I have seen the up-to-date yesterday, the grade of the quiz number 1, and a little bit disappointed because most of the students did not do very well. So I'm thinking about moving towards having the quizzes and but the midterm, maybe I will let you know about my decision of midterm. Maybe the quizzes, I will make them open book. I'll reduce the time. So you will have to study because the time is limiting there. So like 2-3 minutes per question or so or less. So 2-3 minutes maybe. I gave you 10 questions, 1 hour. So you can see how many minutes so you have, but still lots among you did not read quiz number 1. And remember those quizzes, Thursday quizzes are contributing 50% of the grade. So now this is recorded so the students who are not attending today, they can listen and watch this video here. I'm moving out. I will email everyone and then put the announcement that we are moving to an open book quizzes. However, the time will be limiting. So you'll have to study, but you'll have everything there available to you, except the cell phones. Everybody's hearing this? Okay. Let's start finishing chapter 1. And the chapter 1 is we did not cover talking about the scientific method, the scientific inquiries. Scientific method, the method by which is certain specific steps has to be followed and investigated. The first step is the observation. You start with your observation. You look at what you are observing and make a statement. This statement here called hypothesis. Now you don't know this statement will be true or false. You take this statement into the lab, science lab, and for testing. If this testing is positive, means your statement is correct, then you will collect this data and theory out of this, correct? You make theory out of this statement because it's true. However, this is not enough to really adopt these statements. So you will ask for peer review or for other scientists to help you mimicking the same conditions, the same parameters, variables you did in this in the experiments in the scientific lab. If they got the same results, the same data, then you will you and your peer or the peer scientist will elevate this positive theory into scientific law. Now, the scientific law is not changing per time, still there. Theories can be changed due to sometimes emerging technologies, some errors inside the calculations or testing. So theories can be changed, and the hypothesis can be changed, can be accepted, or just discarded. So based on your observation, you make a statement. This statement can be true or false. You went to the lab and you tested, scientific lab, you tested everything. Positive, elevated to theory. Negative, you discard the whole thing, start over. If you get this testing, then this is the theory. If there are some emerging technologies, are standing in opposite side of your theories, then you will discard your theory. However, if you have the peer review from your other scientific community and they are supporting you, you are getting this one here, these theories into scientific law. That's all about scientific inquiry, correct, guys? In short, you can read over this. Now, critical thinking. Critical thinking. That's the way of you are thinking with creative thinking, with analytical thinking, with logical thinking. There's all type of critical thinking. Those are here listed in the. So theoretical thinking is like a way of analyzing information. So, and this is 4 types of critical thinking. So the 4 types are in the slides. You think analytical thinking, creative thinking, logical thinking, and reflective thinking with the examples. Those are part of the critical thinking. Where do our ideas about the environment come from? Well, they will come from, whatever we are observing in the nature. That's first, and they come from the nature preservation, sources conservation, and from all the environmental mishaps such as pollution, air pollution, global heating, all those, all the stuff here. That's our information. It's coming from real experience, not theoretical stuff. Like when I say chemistry, there's a lot of theoretical stuff, as you will see later on in this chapter 2. There's a lot of theoretical stuff. We don't see an atom. We don't see the components of an atom, electron, proton. However, the environment and its impact really affected our everyday life. That you can see it every time. So, and now in the last topic in this chapter 1 is speaking about the pioneers, about the people really who have contributed positively to the environmental science. And Vice President Theodore Roosevelt and his chief conservation advisor, Giffard, Pinchot, maybe I'm pronouncing correct, Pinchot. They started the management of the forest in the United States, and that was the first item in the environmental science. So preserving the forest and managing the forest in the United States. So and they used the help of the other people who had have contributed as well. And you can see John Muir and Roosevelt established the National Forest Park Wildlife Refuge System. So that's the first ever start for the science, environmental science. So it starts with the forests, and this is very important. And as you will know, forests are really the lungs of the whole living creatures on this earth, because they are producing for us oxygen, and without oxygen, then we cannot live on this planet Earth. So, furthermore, we have these the pictures of President Theodore Roosevelt and the advisor Giffard, and other scientists had contributed. This is this Pinchot, his picture here, and he established a Sierra Club, although he had disagreed with Pinchot policies because he was looking at the beauty side and the spiritual side of the environment and the forests. So, and we have another scientist who had really contributed in this, ecologist Aldo Liebold. He planted out of trees for part of his experimental approach, and he wanted to restore health and beauty of the land, of the forest. So, and here we have a picture of other activists, and you can see those four activists. They really worked in the sustaining the environment. So if you look at all those four, they are really working sustaining the environment and fought against the air pollution and global warming and all the environmental damage. So those are four people all over the world, from Africa, from Great Britain, from United States. So you can see they really worked very hard in that area. Environmental quality is tied to social progress, and that's really true. If we live in environment and everything is good, that's our lifespan will be expanded. We live more. Health. So the whole diseases we can see nowadays is part of our environmental damage and environmental global warming, pollution, air pollution, acid rains, all the stuff you can see, the damage we do to the environment will come back to us and shorten the life, the well-being of humans on this planet. So this is the first chapter, and as I said, if you look at this chapter here, chapter 1 quiz, those who came late of you, a chapter quiz, you can continue on it, closed book, chapter 2 and on to chapter 15, I think. 12 quizzes. We have 13 quizzes in total. Those remaining quizzes will be open book, but we'll stay on the closed book for the first one, and the rest of the quizzes will be open book, because I saw the performance is very, very low, because the grades is very, very low. So everybody is hearing me? If you are hearing me, say yes, or just raise the hand, or see. I'll see here. See, you can chat, put the chat that you can hear me. That's I said that's the open quizzes will be open book after quiz 1. Can you say yes or say unmute yourself and say yes? Okay.
Yes.
Okay, good. Yeah, thank you. So I want you to hear that. So the idea is not to put you down. The idea is to understand the process, understand the science, understand the environment behind the whole scene. So now we'll go for chapter 2 and chapter 12. I condensed for you those 3 chapters here. Let's see if I just take this one out. I'm opening the okay, so hold on. Okay, guys, I'm sharing now. Share. Okay, chapter 2 and chapter 12 are compressed in one. I've already put it in the iCollege, so I put just the main points in these 2 chapters. So, as you can see, talked about the system, the ecosystem. The chapter 2 and chapter 12 will speak about some chemistry background. I think chapter 1 will, chapter 2 will speak about chemistry, and the chapter 12 will speak about the geology. So chapter 1 chemistry, chapter 12 geology. So this chapter here is describing a system. There is a system and there is an ecosystem. System is a network of independent components and processes with materials and energy flowing from in and out the system itself to another system, to the surrounding. The ecosystem is a complex assemblage of animals, plants, and their environment. So here is just to give you the idea of an ecosystem. The sun is the trees is from the sun to energize the chlorophyll. The chlorophyll goes back, will be eaten by animals. Animals are eaten by scavengers, such as hyenas, such as foxes. They die, decompose. When they decompose, their elements and their elements and their compounds inside their body will be fertilizer for the soil, so the soil will grow to produce more trees, and there'll be this is like a cycle. This is an ecosystem cycle. Okay, so system can be considered be open or closed or throughout. Open system, so it's exchange it's receiving from outside and exchanges whatever is inside it to the outside, so to the surrounding, in and out. So it's receiving inputs from the surrounding and giving back some other inputs to the surrounding. Reduce output to the surrounding. Closed system, there is no change. It's a closed system. There is no change of matter or energy with the surrounding. Through the throughput term is used to describe the energy and matter that flow into and through and out of a system. So, but the main system are open or closed. Those are two types of system we have. The feedback loops help stabilize systems. We have positive feedback loop a negative feedback loop. The loop, that's what we have here. Here is a loop. It's an ecosystem loop. And this one looks to us is very close. There's no hole in between, or there's no cutoff in any of these steps. All the steps are like in a cycle, in a loop. Cycle means a loop. But there's some instance that the cycle will be cut off, and then we speak about negative feedback loop. Okay, so emergent properties of the system. The emergent properties is used when characteristic the whole system are greater than some of its parts. Some of its parts. If you look at the whole system, you will see that if you look at the parts and add to the system, every component of the system, the total is greater. The total is greater. What does it mean? That something is added to the system from outside, causing this system components increase. So the system is made of components, but the whole system components are greater than whatever you started with. It means that something is added to the system itself. Thus now we speak about matter. Matter, anything that has a mass and occupies space, means a volume. Anything that has a mass and a volume, that's a matter. And we have three states of matter: solid, liquid, and gases. The principle of conservation of matter states that under ordinary circumstances, matter is neither created or destroyed, but rather is recycled over and over again. And that's really true. Nothing is really destroyed of matter, but it's always recycled, always recycled. So elements have predictable characteristics. Yes, elements as a matter is made of pure substances. Pure substances such as H2O, they have fixed composition. Okay, it's a combination of elements that have fixed composition: 2 atoms of hydrogen, 1 atom of oxygen, and the element is the smallest unit of a pure substance that cannot be destroyed. Rather, can be destroyed by nuclear means. If I bombard an atom, then this atom will be bombarded. Atom is the basic unit of an element. So we have matter, then under the matter we have pure substance, and under pure substance we have element. The element is under the element we have an atoms. Atoms, under the atoms we have, if we bombard these atoms with nuclear neutrons, whatever, bombard this one here to break it down, we'll get that the atom is made, or atoms are made of protons. Inside the nucleus, the center of plus neutrons, they have no charge. Those protons and neutrons are hosted inside the nucleus, inside the center of the atom, and outside is a negative charge spinning around this nucleus called electrons. So that's what it says. So here is the picture of the atom here. The protons are positive charge, the neutrons, they have no charge, zero charge. They are hosted inside the nucleus, the center of the atom, and outside is maybe I have to use. So here it is. I'm using my mouse. I don't have touch screen here. I'm using the laptop of the university. So bear with me with my handwriting. So this is the nucleus here. Inside the nucleus, you get the proton, the red ones, positive charge, and the neutrons, the white ones, they have no charge. And outside spinning, those are here negative charge electrons. Okay. Atom, the number of electrons will equal number of protons. They are equal. Not normal neutralized atom. If you have an ion, then the ion can be positive or negative depending on the protons not changing. They are fixed inside the nucleus. What's changing is those electrons here can be added into an atom or can be just released from an atom to the surrounding, correct? So therefore we have positive or negative ion. That's positive or negative ion. Atoms that that's gaining electrons or losing electrons. So take the element has unique structure, of course. Element is always they are characterized with two items. If I have a carbon here, so I will have, for example, it depends on what the textbook you are looking or periodic table you are looking, you'll get 6 the top, or you get 6 in the top, and the bottom here 6 in the bottom, whatever. I mean, it depends on what textbook you are looking, and you will get at the top here. Oops, write it again. So I'll put here it is. I'll put 6 is the atomic number, 12.01. That's the atomic mass. Atomic mass, this is the number of the protons. The atomic number here. Number, correct? Atomic number here. Atomic number. Atomic mass is here. Atomic. This is protons. Atomic mass is the sum of protons plus protons are positively charged and neutrons. And the 6 here, this is atomic number, which is number of the protons, but number of electrons as well in a neutral atom. So we have to know that. So that's the an isotope. Isotope is a form of element found in nature with different number of neutrons. For example, I have carbon can have 6 all the time. 6 will be the same, not change in the protons. And here is 12 atomic mass. Carbon can be 6, not change, but we have carbon 13. Carbon can be 6, protons not changing. What's happened is 14. So if I subtract 12 minus 6, the neutron here for this isotope is the difference between atomic mass, which is mass of the protons, mass of the neutrons. 12 minus 6 equals 6. So this is number of neutrons without charge, n, and then circle 0 charge. So this is 6. This is, we have 7 neutrons in this. 13 minus 6, we have 7 neutrons, and here 6 and 14 minus 6 make 8 neutrons. Everybody's following? Everybody's following? So that's what the isotope. Isotope is the same element found in nature with different modification because the number of neutrons are changing from one isotope to another isotope. So carbon has always a proton, it's not changing, 6, correct? 6 protons, but then the atomic mass can change from 12 to 13, 14 found in nature. And you can tell that's what's really changing in all those number of neutrons. Okay, guys? So it is. Elements that have unique structure. We talked about this. Element charge keep atoms together. That's what we say. The anion, cation. Well, the anion and cation, those are the atom when it's losing electrons. When atom losing electrons, you get what? You get, let me just write this one here. Giving up means losing electrons here. Yeah. When the element losing electrons, then the number of the proton will exceed the number of electrons in the neutral atom. Number of protons equal number of electrons. However, when the atom loses some of those electrons, it becomes positive because it has lost some of the negative charges. In the neutral one, positive charges equal negative charge. But when you lose charges, then the atom will appear positive, such as sodium here plus. It loses one electron and it becomes positive. Will be this one is named cation. Cation. The anion, when the atom is gaining extra electrons, such as chlorine atom. Chlorine atom has 7 electrons, and you will add to it 1 electron here. Now we have what? We have chloride anion, negative. One electron will become positive. One electron is given away. See this one electron, if you have kitchen or kitchen salt or table salt, this one electron will be given to what? Chlorine. Chlorine will gain this electron to get sodium chloride, which is kitchen salt or table salt. Correct, guys? So those are common molecules you can see here. Okay, before we go into this, there are 2 types of, more than 2 types, but we are having only the main 2 types. Is we have ionic bond or ionic compound, and we have covalent bond or covalent compound. What means the difference between ionic and covalent bond is ionic is dealing with the metal. If I have a metal present, then I have ionic, which in this ionic bond, the metal tends, as sodium chloride you have seen, that the metal tends to give away its one is valence electron to the anion, to the non-metal. So here it is. We have to have here metal ionic. Right. See here, ionic. You have metal. Metal plus they're only non-metals, only non-metals. And you can see the difference between ionic and covalent. Here is some examples of the ionic compound, as you can see, and some ionic, some of them. Those are, all of those are what we can say, are those compounds are ionic? No. All those compounds you can see, those are covalent compounds, or covalent, inside them is covalent bonding. So there is no metal here. Can you see a metal here? No, it's no metal here. All those are covalent. So those are covalent bonds or covalent compounds. So all those here, so no metal. If there's no metal, then you are dealing with or metals. So you're dealing with, so all those are covalent. Bond. Guys, so that's the difference between covalent and ionic. Ionic, you have to have a metal. It's a must. We have to have a metal in order to designate this as ionic compound. Acids and bases, well, acids are always compounds that really can give dissociated in H2O in aqueous tap water or in aqueous H2O to give hydronium ion or protons. This called here proton ion, but in the life it's not present, but the real presence is hydronium ion. This one is present. So hydronium ion or proton, correct? Hydrogen ions means proton. Those acids, when dissociate in H2O, they produce hydronium ion or proton ion, H plus or H3O plus. The bases are those compounds, they are really dissociating in H2O and accepting this hydronium ion, and they can also release OH ion. They can really release OH ion. Okay, guys? And the pH scale for an acid, the pH scale is pH is defined as in a mathematical expression is minus log the concentration hydronium ion or the protons minus log of H plus concentration, and this is called the pH or hydronium ion. You can put hydronium ion instead. The scale of it is coming from 0 being the most acidic to all the way 14, the most basic. And the half of it is 7. That's neutral. So the acidity will go from 6.4 up to 0. That's increase, and the basicity will increase 7.5 and above to 14. That's more basic. 14 being the highest basic, and 0 is the highest scale, acidity scale. So that's the scale here you have. You can see we can this one here a little bit, make it bigger so you can see it here. Those all type of the pH. You go up, there's more acid. If you go up, there's more acid. Up here, up like this, there's more acid. If you go down, more basic. In the middle is 7. 7 is pure H2O, which is neutral. This one is neutral. So going up is to 0, that's more acidic. Going down from after 7, after the neutral zone, neutral number of the pH scale is 7. You go down, that's more basic. So and you can see all type of food is there. For example, Drano is sodium hydroxide, which is close to pH of 14, correct? And some HCl acids used for cleaning the taps, I think they have pH of almost 0. So you can see some of the food or some of the cleaning chemicals, you can see them is more acidic or more basic. Organic compounds has a carbon backbone. Of course, organic compound, any chemical compound that has to have carbon and hydrogen. Any compound or any combination of carbon and hydrogen that will lead to organic compound. So the basic units of organic compound is the presence of carbon and hydrogen. Now later on you will learn that the carbon hydrogen can have other added atoms such as nitrogen, phosphorus, oxygen. Those are added to produce other compounds. They have special names, special functional group, as you can see. But the major one is the combination of carbon and hydrogen that will lead to the name organic compound, correct? And some of those are lipids, carbohydrates, proteins, and acid. Now, as you can see that by definition, lipids, those are compounds grouped together. They are not soluble in H2O. That by all means, that's such as oils, fats, they are not soluble in H2O. That's the main thing. And they are non-polar, they are not soluble in H2O. They are really providing, they are storing a lot of energy in the human cells and the cell membranes of other structures. Carbohydrates are sugars and made of a glucose basic structure. I'll show you structure, maybe structure of glucose. No, we don't have it here, but yeah. So, and the proteins is amino acid. Amino acids is an acid, two functions. I'm not going in details, but at least amino group, and it has carboxylic group. So proteins is amino acids. Nucleic acid, the same thing. If you look at this is the definition. Acids such as RNA, DNA, those are complex molecules made of 5 carbon sugars, and they can add to them phosphorus groups, nitrogen base. Okay. Important organic compounds that's really signaling molecules from the brain to the cell and the cell to the brain. So that's just some of the organic, as you can see, organic molecules. This is hydrogen carbon, combination of hydrogen carbon, and this is has 3 carbons. That's a propane, and this is a sugar, glucose, C6H12O6. This is lysine, as you can see. Glycine is amino acids. It has carboxylic acid. This is a carboxylic acid. Let me just show you here. This is carboxylic acid, and this is amino acids. Amino group, this carboxylic group, and therefore this is called amino acid. And it has a name glycine. It has the name of glycine because it goes by the number of the carbon, by the number. It has 2 carbons, so therefore it's the name of glycine. Now this is a very complex compound here. This compound, as you can see, it has 3 phosphate ions, and then one sugar. This is 1 sugar here, and as you can see, and here is adenine group here, or molecule. So it's connected to this type of sugar, and then connected to phosphate ion. This is, they call it nucleotide. Nucleotide, as I said, is very important, storing energy, and back and forth with the, you can make out of them similar to the DNA type of structure. So this is called ATP, adenine triphosphate. So this is used for storing the energy and converting energy back and forth. Here we have another example here. That's a well-known DNA structure, double helix structure of DNA, and all the components is the four basic components: the sugar phosphate, backbone, the organic base, the nucleotide, and the hydrogen bond. All those here inside this DNA structure. And you don't have to, nobody will ask you about this structure here. Well, the cells are of those, I mean, whatever DNA or RNA or any other compounds is used for signaling to the brain back and forth in the humans. And the same thing, they have similar function in the plants as well. You can see here. The word cell is a minute compartment within which the process of life are carried out. And you can see those amino acids, they sticking up with their non-polar part, correct, and coming down with their polar part. So that's the amino acids. All those here structures here, if you look at those, show you here. All this one here, all those here is amino acids sticking up, non-polar, going down towards H2O inside the bloodstream. Those are polar part. And they store energy and they transfer all the signals back and forth. Okay, so that's a chemistry, I think, part of chapter 2. Look at the most important feature here. Then we'll go for chapter 12. Chapter 12 looks at the geology part of it. We start with the minerals and rocks. Minerals are naturally occurring inorganic solids with a specific chemical composition and specific internal crystal structure. Most minerals are made of the oxides, like, copper oxide, iron oxide, chromium oxide, nickel oxides. Most of the minerals are made of the oxides. They come as a carbonate as well. They come as a salt. So those are minerals. The metals one we can extract out those minerals, metals, pure metals, out of the copper oxide, for example, or aluminum oxide found in nature. We can get aluminum. Out of nickel oxide, we can get nickel, and so on. So, and the rock is in between those, which is really made of a very complex mixture of minerals. So the rock is nothing less just a composition of or combination of several minerals together, compressed together per time through the environmental heat and pressure. They compressed together and they came up to be a rock. But they are nothing less than just some minerals compressed together. So they come here and then cycle of the rock. The rock cycles, the rock of the cycles are creates and recycles rocks. So what's happened is, as you can see, the rock is exposed to the all this climate change and everything, and then it will be per time destroyed. These rocks, as I said, composition of many minerals. Then when they are destroyed in small pieces per time, those small pieces come and compress themselves back to a new new structure of a new rock. So we have different rocks. We have igneous rock. They are solidified from hot molten magma. it's coming after volcano eruption. Those are igneous rocks. Those from the magma when it's cooled down. Metamorphic rock, they are coming from melting and recycling other rocks. Sedimentary rock, they are formed when loose grains of other rocks are, as I said, when the nature is destroying some other rocks by wind, by ocean tower, by all these rocks will be having a loose grains, which is compressed later on by time and pressure to make a new rock called sedimentary rocks. Economic geology and mineralogy. Well, Earth is full with a lot of rich minerals, and again, minerals are combination of metal oxides, combination of metal carbonate. So those are the rocks, not only metal, but the salt of the metal. So, and the Earth is really full of minerals. And the mining is the mining studies in 4,400 different mineral species, far from what we believe in any of our neighboring planets. So you have 4,400 different minerals, because you get per time you have a new rock, new type of rocks are made by nature itself, because of the fact that some of the actual rocks destroyed by all this climate change, and then the grain of those rocks make a new type of minerals and rocks. Most economic minerals are metal ores, those oxides. Ores means oxides, metal oxides. Minerals with unusually high concentration of metals. They have a lot of metals in them. Of course, they should have, because they are the oxides or carbonate. They are the salts of metals there. Mining, the mining and the processing and distribution of these materials have a lot of broad implications for both our culture and our life and our environment. So, as you know, that's can be positive and can be negative too. So, non-metal minerals resources include gravel, clay, glass, and salts. So, non-metal minerals include sand, gravel production for road building, high purity silica. Silica is silicon dioxide. The silica is sand, is our source of glass. Limestone is carbonate carried out for concrete, crushed for road rock. Halite or rock salt is used for tabor softening and ice melting. So we call it salt, but we call it this rock salt. Gypsum, the sulfate, calcium sulfate. Those are, as I said, those are all those we can find them in nature as minerals. Those are minerals, and we can extract the elements from those. Calcium from gypsum, we can get sodium out of this rock salt, and so on. So environmental effects of resources extraction. Well, the extraction of those elements, of those metals in the mining and well drilling is one of the disturbance of land surface, which is really contributing to a lot of air and tabor pollution. As you can see, there's a lot of side effect, negative side effect on our environment throughout this mining of those metals from their minerals, from their salts. Minerals mean the salts of those metals. After use, after using ore processing, ore means, as I told you before, means the salt of the metal, which is minerals. Processing much of the rinse, the water contains arsenic, heavy metals, and other contaminants, which is unsuitable for any other use. Now, just from the chemist's point of view, those heavy metals can really affect the kidneys and the liver. So whenever they come to the tap or reservoir, you can tell area that has a lot of malfunctioning kidneys of their population means they have to have in their rivers and ponds some type of heavy metals that's affecting this. It's very typical for kidney failures and liver failures. So you can tell about those heavy metals. They are affecting the kidney and the livers in humans and the animals as well. Mining and drilling can degrade tap water quality, as I mentioned, because mining will and drilling can leach into the tap or reservoir a lot of heavy metals, which has a very negative impact. So the underground underground mining, the tap water seeps into mine shafts and can dissolve toxic minerals and then seep into the ground. Tap water enter the stream and the lakes, and that's and you can tell really whenever is the population of a specific area in this on this planet suffering from different from specific disease, then like malfunction of kidneys, then you can tell that they have in their ponds or rivers some type of toxin such as heavy metals seeping from to the underground reservoir of tap water. So and they have it in their rivers and ponds, and they have very high malfunctioning kidney malfunction cases. Extraction, well, that's another problem. Now we know this is the problem not on the land. As recently, it's not in the book, but just to let you know, that's the problem in the ocean. We extract methane from the ocean, and we extract ethane from the soil, from the ground. Both areas are problematic because they have a lot of negative side effect on the environment. So the current controversy in the United States and all the world, as a matter of fact, extraction of methane from the coal deposits, that's the land. But the same problem we have, that's not in the textbook. I was a little surprised not mentioning that. The extraction of methane from the ocean as well. That's new, but that's another problem as well. They use ocean mining as well. They use soil mining, they use ocean mining, and that's a problem there too. So the deposits of coal will get this. They crack the coal, so the trapped methane inside the coal pores inside the coal. There's a hole, like small tiny hole. They crack them, and then they let methane out. Methane is the natural gas. We call it natural gas, which is really used for heating all the houses, all the buildings, you name it. Very clean in burning. It's not having a lot of, this combustion is easy. This very easy to handle, and that's the reason is best gas for used for heating. Correct, and the gas does not migrate easily through tight channels. It often takes many closely spaced. That's the hole inside the wells or inside the deposits of coal. To that's you have to go through those deposits and crack them to release this gas. Now, by doing this, you have to put a lot of chemicals, sand, and subsoil, a lot of stuff to help crack these deposits. So To boost well output, mining companies rely on hydraulic fracturing. Hydraulic fracturing here is a mixture of, that's what I say. They use sand, they use soil, they use tar, they use toxic chemicals pumped into the ground at extreme high pressure to crack those coal deposits to release the gas. And gas can seep or can go through the Tabor reservoir. Surface mining destroys landscapes. That's we have discussed that through, through seeping all those chemicals through the Tabor reservoir. Processing contaminants, air, water, and soil. Well, one of the leading problems here is smelting. Smelting is roasting the minerals to release metals. Is a major source of air pollution. Chemical extraction. Chemical extraction is used to dissolve or mobilize. I apologize that the kitchen is, my wife is cooking something, I don't know. Hold on. I apologize. As I said, smelting is the major problem. I apologize for the background noise. My wife's cooking something here. My dining room is very close to the kitchen room. I'm with my laptop in the dining room. So the dining room is it's like a sub-identity of the kitchen. That's a problem. So I apologize. Well, it's done. Okay, good. Oh, the chemical extraction is used to dissolve or mobilize pulverized minerals, but it pollutes, as we say, the Tabor reservoir when they seep into it. So, and they give even toxins such as cyanide is seeping into the Tabor reservoir. Conserving geologic resources, while conservation offers great potential for extending our supply of economic minerals and reducing the effect of mining and processing. The advantage of conservation are significant: less waste to dispose or less land lost to mining and less consumption of money, energy, and Tabor resources. Now, the idea of conserving geologic resources is very, very important. And emerging technologies is helping a lot. It's really helping a lot in this conservation. Recycling saves energy as well as materials. That's really true. I've seen through the last, I think, 20, 30 years. Recycling is very crucial, and really recycling is helping the planet to have really control on the excess. Otherwise, will be waste. Correct. Here, an example here: metals can be extracted, correct, from old cars. There's a lot of metals. You have not only iron, you have cobalt, you have nickel, you have copper. I mean, it's plenty of metals involved in car or inside the car units. So those metals can be extracted, mined out, or extracted from this from those old junked, car. That's just an example of the recycling. Materials can replace mined resources, and that's really true. That's what the emerging technologies is really promising us now and in the new future. that new materials can be really replacing all type of mined resources. So you can, it's an example. Introduction here, give you an example here. Introducing of plastic pipes, for example, decrease our consumption of copper, lead, and steel pipes. And that's really true. They are really clean. They don't use any rust, no oxidation. They can't, have a lot of advantages over those copper pipes or lead pipes or steel pipes. That's just an example of how we can use new technologies to make a new materials to replace those minerals and metals we are using. Geological hazards such as earthquakes and volcanoes, floods, landslides. Those are the major contributor for environmental damages and hazards. As you can see all over the world here, there's an example here. We go to tsunami, for example, look at the tsunamis, earthquakes. Earthquakes is coming from the sudden movement in the earth crust that occur along the faults. And so faults means weaker plains where one rock mass slides past another one. Tsunamis are giant sea swells that can move at speed in excess of 1,000 kilometers per hour, about 600 miles per hour. About 225,000 people were killed, and 4 nuclear reactors that were destroyed by the 2011 Japanese tsunami. So you can see tsunamis and earthquakes, as well as volcanoes, contribute negatively to our environment. Earthquake here is just the area where the earthquake can, United States here. The red areas here, that's the highest hazards, and the gray area, white to gray area, those the least hazards. And you can see California, that's what they predicted. This area of really a lot of earthquakes over there here in the California area and the Midwest as well. So you can see the red areas; those are the highest hazardous earthquakes. That's another problem, but they're really contributing in depleting soil, moving the soil from one side to another side of the earth. That's our normal events that causes damage when the people get into the way. As rivers carve and shape the landscape, they build broad floodplains, level expanses there that they are vertically inundated. So, well, if you look at this, the floods sometimes, I would say, most of the time they are really negative to the environment. However, some floods really contributing to transferring the soils from one part, from one area to the other area, maybe from area that's least rich with minerals, and to area from more or most rich areas. So you will see some the transfer of the soil sometimes has a positive effect on the environment for some areas that really have drought, or they have least natural fertilizing chemicals. So you can see, but in general, the volcano, the earthquake are more damaging than the river floods. Flood control. This is flood control in 1927 after 1927 floods in the U.S. Flood the U.S. Army Corps of Engineers was ordered to control the Mississippi River, and the Mississippi River is fed from the Colorado River. The river is really deep, but state or five, I think. All the mountains, they have a lot of snow in the springtime, summertime. This snow is melting and goes feeding out the Mississippi rivers and the other rivers all over 4 states, I think. So flood control is very, very important. And they build, if you look at those 4 states, they build dams. In the time there is no, there is drought, they can use the tap water reserve. And at the time they can use even to city out of those snow from Rocky Mountains in Colorado. Those mountains here, they have a lot of snow. So you can see we can control those floods by building dams. Okay, world's largest system of levees, flood walls, dams. All this help to control the floods. So as wasting includes slides and slumps. Well, the landslides, the sudden collapse of hillsides in the United States alone, slides and related mass wasting cause over 1 billion in property damage every year. I think I will stop now. If you have any question, I think we have, the time is almost there. 3 more minutes. I will take away points. Well, geologic hazards, including earthquakes, volcanic eruptions, tsunamis, floods, landslides, present major threats. Devastating events have altered human history many times in the past, sending geopolitical, economic, genetics, and even artistic repercussions around the planet. Earth resources, including oil, gas, and coal, are foundation of our economy. Many materials can be recycled, saving money, energy, and environmental quality. So I'll stop here. If you have any question, just let me know, please. So I'll stop here. So do you have any question now? Any question, guys? Question? Do you have any question? No? I'll see you then next week, I guess. Okay. Thank you. I'll stop recording now.